Okay, we have lesson 66 today, which is use substitution, change a variable. It is more integrating. The farther we delve into this, the less it is obvious to the naked eye as to what the answer is. There's more things to compensate for, and we have a little bit more variables involved today, which makes a little bit of difference. So we're going to talk through use substitution. We've got some indefinite integrals up top, so we'll have our plus c's. We've got some definite integrals at the bottom to talk about and how that works. Okay? As we look at example 1, integrating 40x times x squared minus 4 raised to the 5th dx. With the use substitution. Okay, as we look at this right now, what are you guys going to tell me in terms of guessing?
It's x squared minus 4 quantity to the 6th.
Okay, when we get done, final answer. Right now, the main thing is x squared minus 4 to the 5th. So the integral of something to the 5th is something to the 6th. So final answer is going to involve an x squared minus 4 raised to the 6th. Now, inside of there, though, we have that x squared minus 4, which involves a chain rule issue. But we also have a 40x out front and all of this business. So with the use substitution I'm teaching today, what I'm going to suggest is you take the insides and make it equal to u. Okay? And it eliminates, I think, more of the guesswork here, and it's more of a set method with the ones we're doing today. So as we look at this, what is the inside?
X squared.
That x squared minus 4, right? That something is what? So what I'm going to do is off to the side here, I'm going to say u is x squared minus 4. I'm picking u to be that inside piece. Now, while we're over there off to the side, we're going to go ahead and take the derivatives of both sides there. We're going to use our differentials. So like the derivative of u is just 1, but I'm going to say 1 du, or in other words, du. The derivative of x squared minus 4
2x.
is 2x. And then I'm going to tag on a dx. Now, I'm going to kind of pause that there at the moment. And we'll come back and see if it matches up or if we need to do a little bit of moving around. So we're going to go over and integrate here. And as we go over and integrate, first of all, x squared minus 4 is going to be replaced with u. So instead of saying x squared minus 4 to the 5th, I'm going to call this u to the 5th. Okay, so that is that piece right over there. As we look at the constant of 40, what do you know about a constant of 40? What?
Push it out.
Yeah, it can go out front, can't it? Okay, so a coefficient of 40, easiest thing to do with that is we're going to say, okay, it's just a constant. We can't do that with a variable involved. But with a constant, a plain number, we can move it outside. Now, what we need to figure out, what other pieces have I not accounted for yet? The x and the x dx. So this is where, go back to our side work. What does x dx equal? So 2x dx
So x
equals du.
equal to 2.
So how can we make this just be x dx equals?
Divide by 2.
Divide by 2. And so the idea here is that x dx is going to equal, and there's a couple different ways you can write it. And I'm going to say du over 2 for this purpose. You could also, if you prefer, that is 1/2 du. But the idea is I was trying to get x dx here to match up here. Because now, in other words, everything has to be taken care of is not the best phrase. But everything has to be replaced or equivalent. There has to be something representing every piece. The 40 I moved out front. X squared minus 4 to the 5th is now u to the 5th. X dx, well, this needs to be in terms of u because we also need one variable. X dx is equivalent to du over 2. So that is u to the 5th times du over 2. Can you feel confident that everything got replaced? Everything has something representing it. That's what you need to make sure of every time. Now, to clean this up and make it a little bit nicer before we do anything else, and it's not that you have to do this, but this 2 in the denominator, it's just a constant, yes? A 2 in the denominator is representative of a 1/2. I would pull this 1/2 out front with the 40. Or in other words, not that you have to write it like this long term, but I'm going to write it as 40 over 2. That way you still physically see the 40 and you still see the 2. And then that means I'm doing the integral of u to the 5th du. Is that something you can integrate? Definitely, right? So out front, if you haven't already, 40 divided by 2 is now 20. What is the integral of something raised to the 5th? Not quite.
Oh, yeah.
Yeah, actually, no, you totally went the wrong way
Yeah.
there.
1 over 6.
Yeah, it'd be
Yeah.
6 over 6.
So you add 1 to the power, so it's u to the 6th, and you divide by 6. So you can say 1/6 u to the 6th, or if you prefer, you can say u to the 6th over 6th. And officially, of course, we're not quite done, but we still need to go ahead and say it's an indefinite integral plus c. Now, I say we're not done for 2 reasons. One, 20 times 1/6 can clean up. But here's the other thing. We were integrating in terms of x. Our answer needs to also be in terms of x. So this is where we're going to go back and we're going to substitute. U was x squared minus 4. So now we're going to replace that. We're going to have, there's still 20 out front, there's still 1/6. Maybe you've cleaned that up. I'll get it here in a moment. Instead of u to the 6th, I'm going to say x squared minus 4 to the 6th and plus c. I would definitely clean that up for final answer. Again, you may have already. 20 times 1/6 is 20 over 6, which reduces to be 10/3 times x squared minus 4 raised to the 6th plus c. Okay, what questions do I need to answer?
So could you not do this by guessing?
You could. I'm not going to say you couldn't. I think the more we delve into this, there's just more to keep track of. There are some problems where I don't think you'd want to do it by just guessing. So, no, I'm not going to say that, with enough practice and whatnot, that you couldn't look at this and see it. I'm not going to say that at all. And some of this just, each problem's a little different. It's trying to give you the tools here, right? And some people are saying, Ethan, you're crazy. No, I don't want to do that by guessing. I like what I just did. And others of you saying, this is ridiculous. Let's go back to guessing. So I'm guessing you have people on either side of the fence here.
Honestly, I think I like having the more methodical way because, I'm confident in my guesses most of the time, but there's still some where I'm like, is that what that equals?
Exactly. Some of you like the method, some of you like the guess. So, okay. Try example 2. So, if we're thinking about guessing here, as again, I'm not really going to guess today, but still, if we're thinking about guessing, you need to be able to identify what is the main thing we're integrating there. Yeah, that square root in the denominator, right? So it's that square root, so that power of negative 1/2. So, yeah, you could go ahead and look ahead and say, okay, my answer is going to be something to the positive 1/2. But the reason I'm asking you this is, what am I going to use for u? What is the inside? B plus sine of ax, correct. So I'm going to come off to the side here. And my u is going to be the inside of that radical. So b plus sine of ax. Now, I didn't read the problem out loud to you because I figure you guys can read at this point in your lives. But notice a and b are what? Constants. So you have to think of a and b as numbers. When you take these derivatives and do these integrations, they are numbers. Okay? Okay, so either now or later, let's go ahead and take the derivative of u. Derivative of u is du, just 1 du. Derivative of b plus sine ax.
A cosine ax.
And then a dx. Okay, so the derivative of b is 0. It's gone, right? Because the derivative of b is just 0. And then the derivative of sine of something is cosine of something times the derivative of something. What's the derivative of ax? A. And then because we're working with these integrals, we're going to say times dx. Now, how Ross said it when he said a cosine ax dx, that works as well. And that's how I would normally write it in a simplified form. Okay, so definitely fine with that if you put a cosine a of x. I'm not going to mess with that anymore, though, until we see what needs to be in the equation. So let's go to our integral and see where we're at here. Let's see. How do I want to do this? First of all, my u is right there, yes? So the main thing we're going to be doing the integral of is the integral of u to the negative 1/2, yes? Okay. What am I going to suggest you do with the 20? I'm going to suggest you pull the 20 out front. And then what is not accounted for yet? What do we have to make sure matches up when we substitute in our du?
Cosine ax dx.
Okay, cosine ax dx is what I need to replace. So what's equivalent to cosine ax dx? So do you see we have an extra a there? So we're going to have to divide that over, and that's going to be over with the du. So du divided by a is equivalent to cosine of ax times dx. And so now to replace the cosine ax dx, I'm using du over a.
And can we do the same thing where we take the a and pull it out?
Yes. So the question was, can we do the same thing and take the a and pull it out? And I would definitely encourage you to. As you get better with this, you might already put the a out front. You know, there are definitely steps you can speed up here as you know, depending on you. So if we go ahead, I'm assuming that's what I did. We already have a constant of 20 out front. This divide by a is a constant, so 20 over a times the integral of u to the negative 1/2 du. (20 over a stays out front. What is the integral of u to the negative 1/2?
U or B 2 to the 1/2.
You could say 2u to the 1/2. Are we all okay with that? Because I'll be honest, in my notes I have it written as u to the 1/2 divided by 1/2. That's kind of taking us back to how we first learned it, but u to the 1/2 divided by 1/2. Yes, I agree. The better way to write that is 2u to the 1/2, right? Because dividing by 1 over 2 is multiplying by 2 over 1. And then don't forget to say plus c. The earlier we put the plus c in there, maybe the less likely we are to forget it. So definitely, if we take that 1/2, it's multiplying by 2. That's going to make it 20 times 2, so 40 over a, if you will. U to the 1/2 plus c. Except we started in x, we want to end in x. So 40 over a times something to the 1/2. What was u? B plus sine of ax raised to the 1/2 plus c. In my notes, I just have it raised to the 1/2. However, did you put under a square root? It's perfectly fine if you did. I don't care either way. As always, my response is, are you aware of the equivalence, right? Okay, moving along. Example 3. Integrate 7x square root of x minus 1 dx. Okay. You realize we're integrating something to the 1/2. So what is my u value? Okay, the insides, and so x minus 1. If u is x minus 1, then du is 1 dx, or in other words, just dx. Yes, that is the way it works out on this one. Okay. Let's write out our integral. Let's see. It's the square root of x minus 1. So it's going to be the square root of u, or in other words, I'm going to say u to the 1/2 when I replace my x minus 1, right? The 7 is going to go out front because I'm just, everything I can get out of the way I want to. And then what is unaccounted for? X dx. What do I have over here? Dx equals du. What? No, because because there's not two sides here. Oh, you're talking about over there?
Yeah.
No. I'm trying to think of a good explanation of why you can't, but probably just because x is a variable, not a constant. So, okay. There's a slight obvious change here, right? Okay. The dx is going to be replaced with du. But the problem we run into is we still have this x that isn't accounted for.
But we can, in theory, solve for x, right?
Ding, ding, ding. We know, we made the statement that u is x minus 1. If u is equal to x minus 1, do some basic algebra 1. And according to u being x minus 1, what is x equivalent to? If you add 1 to the other side, it is equivalent to u plus 1. So I can take my x right here and replace it with u plus 1. That's a little trick that happens sometimes when you have an extra variable there. But if you have an extra variable like that, you should be able to go back to your u statement and manipulate it. Now, when we go to integrate this, we don't want to integrate yet. We want to use another algebra 1 skill. We want to take this u to the 1/2 and we want to distribute. And that will make the integration much better. Okay? Because then we're just integrating two separate terms. So keeping my 7 out front, what is u times u to the 1/2? U to the 3/2, because this u is a u to the first. U to the first times u to the 1/2. You keep the base of u and add the exponents, right? I know I'm really making you guys dig deep, aren't I? So this is u to the 3/2 plus, this one's easier, 1 times u to the 1/2. Okay, u to the 1/2. And then du. It's not fun integration, but it's not horrible either. So I'm going to keep my 7 out front. What is the integral of u to the 3/2? Add 1 to the power and divide by the new power.
Over 2 to the power of 2.
Flip one of those, but yes, half right. So if we add 1 to the power, 3/2 becomes 5/2. You're dividing by 5 over 2, which is really multiplying by 2/5. So 2/5 u to the 5/2 plus integrate u to the 1/2. So add 1 to the power and it is u to the 3/2. Divide by 3 over 2 is multiplying by 2 over 3. In that parentheses, and I'm going to say plus c. Okay. 1, don't forget to substitute what u is. And then I have in my answer key this distributed. So I have that I distributed the 7 in and said 14/5 u to the 5/2 plus 14/3 u to the 3/2 plus c. That's just distributing the 7. Then if I put my u value back in, 14/5 times x minus 1 to the 5/2 plus 14/3 times x minus 1 to the 3/2 plus c. Okay. This is u substitution with our indefinite intervals. The key here is remembering a plus c, and remembering that if you start the problem in x's, you most likely need to end the problem in x's, unless they didn't ask you to. And you might see a multiple choice question where they don't want you to go back to x's. That's possible. Now, the bottom section, you'll notice, is definite intervals. And so we're still going to use the same idea of u substitution. But we have two choices of how we finish this out. And I'm just going to teach one of these ways, but they both, I mean, you can make sense of either way. What you need to remember, these values right here, this integral is in terms of x, right? So this right here, this 0 and this 1 are x values. So one option is like what we were doing up above. Once we do all of our work in u, we go back and substitute in our x's. And then we can substitute in and evaluate from 0 to 1. The other option, which is the one I tend to teach more, is rather than have to go back and put the x's in, which is usually a little bit uglier version, we can change these values to represent u values. And so I'll kind of explain when we get there what I'm doing. But so you do have two options. Both are very acceptable ways to do things. Now, okay. We're going to be integrating what here? Okay, well, the main thing is the sine is what we're going to integrate, right? What is my inside that I'm going to make u? Okay, my u is going to be pi x squared. That's the inside, so I'm still making u that inside. If u is pi x squared, then what is du? Pi is a constant, remember, so you're multiplying the 2 out front. 2 pi x dx. Okay, let's rewrite our integral over here. Now, I'm not going to write the 0 and 1 on there because I'm getting ready to write u's. And those 0 and 1 are x values. Okay? Sine of pi x squared is going to be sine of u, yes, because that is u. Actually, I'm going to scoot that over a little bit. I don't really want it that far. Oh my goodness. I think it might be my shirt sleeve, like making random extra spots. Oh, that's annoying. Okay. Sine of u, which is sine of pi x squared then, right? What do we have to account for? X dx. So if we go over here to our side, x dx. What is x dx? Divide that 2 pi over. And x dx is indeed du over 2 pi. So this is going to be sine u times du over 2 pi. Okay. What I like to teach here is at this point, I'm going to change those 0 and 1 values. I'm going to convert them to u values. Okay? And so in order to do that, we have to have a connection between u and x, and that is this right here. U is equivalent to pi times x squared, yes? And so when x is 1, u is pi times 1 squared. Do you see what I'm doing there? When x is 1, u is pi times 1 squared, or in other words, u is pi. So my top boundary was 1 in terms of x. What is that equivalent to in terms of u? My top boundary is now a pi. My bottom boundary as an x value is 0. When x is 0, u is pi times 0 squared, which just so happens to be 0. So my bottom boundary actually stays 0. And that's just, sometimes it does, sometimes it doesn't. By us changing that 0 and 1 to 0 and pi, we are now done with x. We will never substitute x back in. We are working the rest of this problem in terms of u. Okay? That's what we've set ourselves up to do here. The other option is to integrate, and then you have to substitute the x back in before you put 0 and 1 in. So, huh?
We just murdered that.
I murdered x.
I was thinking,
Okay.
but in my head, this is easy to remember because you're leaving the x and focusing on u. Kind of good.
Okay. This denominator of 2 pi, I'm going to move out front as a constant, and I'm going to make it 1 over 2 pi. So then I'm doing 1 over 2 pi times the integral from 0 to pi of sine u du. That plain nice u is a lot nicer to work with than pi x squared, is my opinion. What is the integral of sine of u? So we're going to have 1 over 2 pi times negative cosine u. And I'm going to say evaluated from 0 to pi. Okay? And now we're just going to finish the problem out. If you did not change to 0 and pi, here's where you have to take your u, and you have to put pi x squared back in. And so then you'd be doing negative cosine of pi x squared from 0 to 1. The u sounds nicer to me. And I will say, you do see some multiple choice problems where they ask, okay, what is this, when you use u substitution or something. So, okay, let's see. 1 over 2 pi, it's going to be the negative cosine of pi minus the negative cosine of 0. Over 2 pi out front just keeps carrying down. Cosine of pi, and here's what my brain does. That's what I'm visualizing. So for me, cosine of pi is negative 1, but the negative of negative 1 is positive 1. Minus negative says plus. The cosine of 0 is 1. That's what I'm visualizing in my brain. Use the quadrantal angles if that's your preference, right? So what do we have here? 1 over 2 pi times 2. Final answer, 1 over pi, and I'm assuming, yeah. When you can do the whole problem without picking up a calc there, we usually just leave our answer as 1 over pi. Questions? Okay, I've got one more example. I don't have a ton of extra time, but we talked today at the beginning too, so. Okay, we're going to try this same method. Use the method of change of variable. That does say 0 to pi, doesn't it? Yes. The integral from 0 to pi of e to the sine of 5x cosine 5x dx. Fun stuff. What's the main thing we're integrating here?
It would be the e to the sine 5x.
Yeah, e to a power, right? E to some power. That's the main thing we're going to end up integrating. So what is my u substitution? What's my inside? The sine of 5x, yep. It is an x. So, okay, u is going to be equal to sine of 5x. Okay, what is du? The derivative of sine of something is cosine of something
Times the derivative of that something.
times the derivative of something, so times the derivative of 5x, which is 5, times dx. You might be getting experienced enough right now that you already know what's going to have to move. I mean, this one's not as difficult to see as some. So if I go over here and I start working on my integral, e to the sine of 5x, well, that's going to be e to the u. What about cosine 5x dx? We're going to have to just move the 5 over to join the u. So du divided by 5 is set to replace cosine of 5x dx. So this is going to be the integral of e to the u times du over 5. Now, keep in mind, these boundaries of 0 and pi, they are x's. If I don't want to have to go back in and sub in that sine 5x again, which that's just going to make things nastier, right? That's kind of the reason we have this option. Okay. So u of sine 5x. Let's see. When x is pi, u is sine of 5 pi. Well, sine of 5 pi, what's 5 pi going to be equivalent to? A pi. Remember, 1 pi, 3 pi, 5 pi, 7 pi, all those are equivalent, right? All your odds. So now, sine of pi. Sine of pi is 0, so sine of 5 pi is 0. So my new upper boundary is 0. Okay. When x is 0, u is sine of 5 times 0. What is sine of 0? 0. So now my lower boundary is 0. So you could stop now if you want, if you know the answer. If you want me to, I'll go ahead and this 5 in the denominator is a 1/5 times the integral from 0 to 0 of e to the u du. You can work it out the rest of the way if you want. I'm not. What's the special rule here?
So since it's 0 to 0, that integral would be equal to 0, right? It's not covering any distance.
Anytime your boundaries are the same, your upper and lower limits are the same, your integral equals 0. And think ahead. If we had gone ahead and integrated, it'd be e to the u from 0 to 0. So then you're doing e to the 0 minus e to the 0. You're doing something minus itself. And then you're multiplying by that 1/5 out front. But something minus itself is 0. So are you seeing where I'm just saying just stop? we could have stopped up above. Once you see that your limits are the same, answer 0 unless we've got anything to add or subtract. So I saw some of you writing it down. I have a note here in mine. When upper and lower limits are equal, the integral equals 0. That day when we had all those properties, right? This was one of them. Now, if you stop and think for a moment, to me, it's logical. Okay? As Ross, Ethan, someone said, it's going from 0 to 0. You're covering no area. So it has to be 0.